Check it out now, y'all.
nanoHUB-U, online instruction.
Welcome to Lecture 3. So in Lecture 3, we get a chance to apply some of the theory that we've been developing over the previous two lectures. So we're going to talk a little bit about thermoelectric devices and materials in Lecture 3. Now, before we jump into Lecture 3, let me just remind you of these equations that should be becoming familiar to you now. We have the two coupled current equations for the electric current and heat current carried by the electrons. And we have a heat current carried by the phonons that we'll discuss in Lecture 5. And we've seen how to derive the various transport coefficients that appear in these equations. At first, I'm sure they looked very mathematically imposing, but once you get used to them, they're not at all hard to understand. The differential conductivity is a measure of how easy and how much current flows at a specific energy. It's related to some fundamental constants we call the quantum of conductance, to the mean free path. The larger the mean free path, the easier it is for current to flow, to the number of channels that are at that energy, and then to this window function, which tells us the region of energy over which F1 and F2 differ. That's the only region over which current flows. So we integrate that differential conductivity across all of the energy channels. We get the total conductivity, take 1 over that, and we have one of our 4 transport coefficients. We've seen that the Seebeck coefficient and the Peltier coefficient are related by this Kelvin relation. Both of them are related to the average energy at which current flows with respect to the Fermi level. If the current is flowing above the Fermi level, we have a negative sign for those two coefficients. If the current is flowing below the Fermi level, as in the valence band, we'll have a positive sign for those two coefficients. And then finally, we have the electronic thermal conductivity, which is a little more difficult to derive. It's related, this electronic thermal conductivity is what we measure when we open circuit the device electrically. It's related to the electronic thermal conductivity that we measure when we short circuit the device. And that one is easier to compute. Again, it's just a function of this differential conductivity weighted by energy minus Fermi energy squared. And then with this expression, we can convert it to the thermal conductivity that we need. So those are our equations, and we're ready to begin using these equations. Now, I'll just remind you that even though the equations look very complicated, we can re-express those equations in another form, and we'll go back and forth between these two forms. So you should get familiar with both forms. We can write the conductivity as the quantum of conductance times the average number of channels in the Fermi window times the average mean free path for those electrons. We can also write it traditionally as electron density times charge on an electron Q times the mobility. Seebeck coefficient, we can't write that any more simply than we did on the last slide. Peltier coefficient is intimately related to the Seebeck coefficient. And the electronic thermal conductivity is proportional to the electrical conductivity. And there's this factor, the Lorentz number, that gives us that connection between those two conductivities. We'll see in Lecture 5 that we can write the lattice thermal conductivity in a form that's very similar to the electrical conductivity. Okay, so now we're ready to begin using these equations. There are 3 things we want to discuss in this lecture. The first is very briefly to touch on thermoelectric devices. Professor Shakuri will be talking much more about that in the subsequent lectures. We will want to discuss then the thermoelectric figure of merit, Z times temperature, T. This is a figure of merit that determines the performance of a thermoelectric device, and then we'll talk about some material trade-offs to optimize that figure of merit. So here's a simple generic thermoelectric device. It consists of an N leg and a P-type leg hooked up in electrical series, and thermally they're in parallel. Now, if I operate this device by injecting a current in the bottom of the N leg, the current will flow up the N leg. Now, because electrons are negatively charged, it means electrons are flowing down the N leg. Those electrons are carrying their heat with them, so we're carrying heat away from the top and dumping it on the bottom. We have Peltier cooling on the top plate, Peltier heating on the bottom plate. The top gets cooled, the bottom gets hot, and we're making a Peltier refrigerator. Now the current goes across the conductor on the top and then down the p-type leg. It's easiest to think about this in terms of holes. In this case, we have holes flowing down. Those holes are carrying their thermal energy with them, so they're adding to the Peltier cooling at the top and adding to the Peltier heating at the bottom. And then the current flows out the bottom leg. So it's relatively simple to understand the basic operating principles. 3 questions that we have then about this device are, what determines the maximum difference in temperature we can get from the cold to the hot plate? How much heat flux can we pump? And what is the coefficient of performance, which is just the efficiency? So if we look at the coefficient of performance when we're pumping the maximum heat, we'll define that as eta. It's the maximum heat that we can pump divided by the electrical power input. And we'd like to design this device to be as efficient as possible to convert as much electrical power into heat pumping as we could get. Now, there's another way to look at this. You'll remember that when we derived the thermoelectric transport coefficients, we only talked about electron flow. Electrons were flowing above the Fermi level in the conduction band, or electrons were flowing below the Fermi level in the valence band. Sometimes people like to think about that in terms of holes instead of electrons. We can go back and forth between those 2 equivalent descriptions. I just explained to you how you think about this Peltier cooler in terms of hole transport in the P-leg, but how would we do it all in terms of electron transport everywhere? Okay, well, we think about it this way. So the current is flowing out the leg connected to the bottom of the P-leg. That means electrons are flowing in the P-leg. So when electrons flow in, the metal contact is shown here in the shaded black rectangle. Current flows at the Fermi energy, or very close to the Fermi energy in a metal. That's where the Fermi window is. When it gets to the P-type leg, the electron has to hop down and fill up an empty state or a hole in the P-type leg. Since it hops down, it releases some thermal energy. That's the Peltier heating that's going on at the bottom of the P-leg. Electrons flow up the P-leg. That's like holes flowing down. When they get to the top of the P-leg, the electrons have to find an empty state near the Fermi level of the metal. They have to absorb thermal energy to get up there and into the metal contact. Once they absorb thermal energy, they're contributing to the Peltier cooling at the top plate. Then the electrons go across the top strap, which shorts the 2 regions, and electrons begin flowing down the end leg. So when the electrons flow down the end leg, the metal makes a contact to the conduction band in the end leg, not the valence band. Electrons have to hop up from the Fermi energy in the metal to near the bottom of the conduction band in the semiconductor. And to do that, they need to absorb thermal energy. So that's additional Peltier cooling going on at the top of the end leg. And then electrons flow down to the bottom of the end leg. When they get to the metal contact, they lower their energy and drop down near the Fermi energy in the metal. That releases heat, and that's the Peltier heating at the bottom plate. So that's an equivalent view of how this Peltier cooler works, all in terms of electron flow. Now we could use this device in another operating mode. We could use it to convert heat to electricity. The way that would work is we would maintain the top plate hot. We would keep the bottom plates cool. Electrons and holes both want to diffuse down a temperature gradient, so they'll want to diffuse away from the hot plate, down. If they're diffusing down the end leg, that's a current flowing up the end leg. Across the metal strap, holes flowing down the P-leg is a current flowing down the P-leg. Flows out the metal strap on the bottom. If we hook up a complete circuit, run that current through something useful like an electrical light or a motor or whatever we're trying to drive, and then bring the current back in the end leg to complete the circuit, we have a thermoelectric power generator. So that's the second class of thermoelectric devices. And the kinds of questions that we would ask about this device is, how much heat flux can we convert into electricity? What determines the efficiency of that process? So the efficiency is just the electrical power out divided by the heat power in, and we'd like to understand how do we optimize a device to make it as efficient as possible. Now, Professor Shakuri will be talking much more about this in subsequent weeks. We want to take just a quick look at it so that we can understand what material properties are related to the performance of this device. And what we'll find is that if we analyze these devices, we will find that all of the material parameters are lumped together in a certain figure of merit. If we multiply that figure of merit times temperature, it's dimensionless. And that dimensionless figure of merit, Z times T, is a very useful way that people think about thermoelectric materials. So instead of getting into a detailed analysis of a complicated device, I'll let Professor Shakuri do that later on, we'll analyze a very simple device and see if we can deduce this figure of merit. Okay. So this is just one leg. Let's just connect one leg to an electrical circuit. We attach a voltage, put a current in the bottom, let the current flow up the top. We'll get Peltier cooling at the top. We'll get heating at the bottom. The current is flowing up, so electrons are flowing down. And the question that we're going to ask is, what is the maximum temperature difference we can get between the cold terminal at the top and the hot terminal at the bottom? And we'll see that that is very simply related to the material parameters. So the way we think about this is we've got a heat flux coming in at the top. We have a heat flux being dissipated at the bottom to the environment. We have some resistance of the electrical leg itself. Since we have some resistance, we have some power dissipated in the N-type leg, I squared R. And we'll assume that half of that flows down to the hot side, half of it flows up to the cool side. And then our task is to analyze the performance of this device in terms of all of these various contributions and see if we can determine what the maximum temperature difference is. So the way we do this is we just set up a balance equation for the heat flux. So if we ask ourselves, how much heat can we extract from the cool side? How much can we absorb from the environment? That's Q sub C, the heat flux at the cold side. Well, that's going to be equal to the heat flux that we're pumping due to the Peltier effect in the N-type leg. But it's smaller than that, because once the bottom side gets hot, heat will diffuse from the hot side to the cold side and subtract from that. So we have to subtract the heat diffusing down the thermal gradient. Now we also have these I squared R losses in the N leg itself. That will generate heat in the N leg. Half of that will flow back to the cold side, so we have to subtract that out as well. So we can write a little equation. The heat flux that we're pumping from the cold side is equal to the Peltier heat flux we're pumping minus the thermal back diffusion minus half of the I squared R power loss. That's just a balance equation that accounts for all of the flows. Now we could ask ourselves, what is the biggest heat flux that we could pump? If my current is too low, I won't be having much Peltier cooling. If my current is too high, I'll have a lot of I squared R resistive power dissipation. So there's some optimum current. I can find that optimum current just by differentiating this heat flux with respect to current, setting it equal to 0. That will give me the current that I should operate this device at to pump the maximum amount of heat. Now, once you do that, we could say, if we have the maximum temperature difference possible across this device, then the heat that we pump will be balanced by the backflow, and we won't be able to get any additional temperature drop across the device. So when the net heat flux pumped is 0, we will be operating at the maximum temperature differential of this simple little device. And you do the mathematics, and what you'll find is that the maximum temperature difference is 1/2 a quantity Z times temperature squared. This quantity Z is the thermoelectric figure of merit. It's Seebeck coefficient squared times thermal conductivity, or times electrical conductivity, divided by the total thermal conductivity, both phonons and due to electrons. So that simple analysis tells us the performance of this simple device is related to a very simple combination of material parameters. When we analyze more complicated devices, we'll find that we come to the same conclusion. So this thermoelectric figure of merit is a really important quantity. If I multiply it by T, it will be dimensionless. So it's Seebeck coefficient squared times times electrical conductivity times temperature over thermal conductivity. And the bigger this is, the more efficient the device is. Now the denominator is mostly determined by the lattice thermal conductivity, because in semiconductors, most of the heat flow is due to the lattice, not to the electrons. We'll discuss that in lecture 5. The numerator is determined by the electrical performance, and we'll discuss that a little bit. And the two questions that we have are, what material properties are needed to give us a high ZT? And given a material, how do we optimize the figure of merit ZT to get the highest value that we can? We'll be focusing on the numerator. The denominator is something that we'll discuss in lecture 5 when we get to phonons. Okay, so let's look at the numerator. The numerator, the term S squared sigma, is called the power factor. And you can see that we need a large Seebeck coefficient and we need a large conductivity to get a large power factor. Now if we look at this, remember our Seebeck coefficient is related to the difference in the energy at which current flows with respect to the Fermi level. So we would like the current to be flowing at an energy that is much higher than the Fermi energy. So if we have an N-type semiconductor, we'd like a non-degenerate semiconductor. We'd like the Fermi level to be way below the conduction band because most of the current is flowing near the bottom of the conduction band. If we look at the conductivity depends on the number of channels that are occupied and the mean free path. In order to get a lot of channels occupied, we'd like to bring the Fermi level up close to the conduction band or even inside the conduction band. That puts the Fermi energy inside the band where there are lots of channels and gives us a high conductivity. So we need a Fermi energy way below the bottom of the band in order to get a high Seebeck coefficient, and way above the bottom of the band to get a high conductivity. And that's the fundamental trade-off that we have. We have to compromise between those two and get the maximum possible product of S squared times sigma. So this is what a typical curve might look like. If we plot Seebeck coefficient versus conductivity, for a P-type material, the Seebeck coefficient is positive. For an N-type, it's negative. There is this region where if the conductivity is very, very low, say I have an intrinsic semiconductor where the Fermi level is near the middle of the band gap, I have both electrons and holes contributing to the current and to the Seebeck coefficient. And I'll find that since the Seebeck coefficients are negative for electrons, positive for holes, they cancel each other out and I get a small Seebeck coefficient in that regime. Now, if I look at P-type materials, if I get the Fermi level up away from the middle of the band but closer to the valence band, I can get a large Seebeck coefficient. I can get a large magnitude of the Seebeck coefficient if I have the Fermi energy in the top half of the band for N-type material as well. But you can see I still have a low conductivity. I'm way down here. Now if I go to a very high conductivity, I push the Fermi level way deep inside either the conduction or valence band. Now I have a high conductivity, but I have a very low Seebeck coefficient. So that's the fundamental trade-off that we have to struggle with, is this relation between the Seebeck coefficient and conductivity, which depend oppositely on the location of the Fermi level. Okay, so if we plot the power factor versus Fermi level, say for an N-type material, plot the magnitude of S, the higher we bring the Fermi level, the smaller the Seebeck coefficient gets. As we become more and more metallic, it approaches a small number close to 0. If I look at the conductivity, when the Fermi energy is way below the bottom of the band, the conductivity is low, and then it gets higher and higher as we go into the band. Somewhere in the middle, there is an optimum of that product called the power factor. That's where we would like to operate the thermoelectric device. We would like to position the Fermi level so that it is near the band edge so that we get both an acceptable Seebeck coefficient and as large a conductivity as we can. Okay, so the peak always occurs near the band edge, and for a given material then, we will try to either dope it or through growth conditions and native defects that occur, we'll try to position the Fermi level so that it's close to the band edge and we get an optimum power factor. But then the other question is, how does the power factor differ between different materials? So given a material, we know where to put the Fermi energy to get the biggest power factor. But how does that optimum power factor vary between different materials? Well, if we look at the numerator, we want materials that have a high mean free path, or high mobility. That gives us a high conductivity. This fundamental trade-off between the Seebeck coefficient and the conductivity, this depends a little bit on the details of the band structure and how the channels are distributed in energy. We might be able to play with that a little bit, and there's some interesting work going on. People are working very hard to try to improve that trade-off, and there are some materials that have a little better trade-off than other materials. If we look at the denominator, we want to find ways to decrease the thermal conductivity, since most of the thermal conductivity is due to the lattice. Most of the success recently has come from engineering the lattice thermal conductivity to make it as small as possible. Okay. Now, let's take a quick look at, just as an example, at bismuth telluride versus silicon. Why is bismuth telluride a good thermoelectric with ZT about 1, and why is silicon a poor thermoelectric with a figure of merit that's about 100 times smaller? And if you look at that, you'll find that the electrical parts are relatively similar, but the lattice thermal conductivities are much different. The lattice thermal conductivity of silicon at room temperature is about 150 watts per meter Kelvin. The lattice conductivity of bismuth telluride is about 1.5 watts per meter Kelvin. So the figure of merit for bismuth telluride is about 100 times better because its thermoelectric, thermal conductivity is about 100 times smaller than silicon. Okay, so about ready to wrap up. We've been focusing on trying to understand this thermoelectric figure of merit, how to optimize it for a given material, how to select the material that will have the biggest possible thermoelectric figure of merit. Good thermoelectrics tend to have very low lattice thermal conductivities. The recent progress, the recent very significant progress that's occurred over the last decade or so has all been about engineering the lattice thermal conductivity, and we'll talk a little bit about that in Lecture 5. Now, many ideas for improving the numerator, the power factor, have been proposed. That's turned out to be tougher to do anything significant to the numerator. But success in the future in continuing to improve thermoelectric figures of merit is going to demand that we learn how to significantly improve these power factors. And there are lots of interesting ideas that are being explored there. I'll mention a few in the next lecture, and Professor Shakuri will talk about some during his lectures as well. So that wraps up Lecture 3. We've talked about these 3 topics: a quick introduction to thermoelectric devices, a derivation of the figure of merit that plays a really important role in thermoelectric science and technology, and a quick discussion of the various material trade-offs involved in optimizing that figure of merit. So thank you, and we'll continue the discussion in Lecture 4.